the reason I choose the subject of the talk was actually came from the Oleg Grigorievich interest, because I choose for my talk the subject stochastic semigroups and stochastic calculus together. So let me start. Maybe everybody can see my whiteboard, and I will use it instead of slides. So what will be the subject of my talk? It is a semigroup of random strong operators. What is it? Suppose that H is a Hilbert space. H is a Hilbert space. I will say that H during all talk will be real and separate. Now consider the operator A, which acts from H into the space of square integrable random elements in the same space H. So if I take some element from here as A from this element, I will have square integrable random elements at the same space H. And I will suppose that A is continuous in square mu. Such an object was introduced firstly by Skorokhod in the middle of 70s. And the reason why we are interested in this object is the following. This is not a family of good bounded operators indexed by the elements of omega. Usually, when we say some random object, we just imagine the set of such objects indexed by the points of omega. This is not a case. See, very simple but good example. Suppose that I have IID standard Gaussian variables, and En, this is orthonormal basis in H. Then one can define operator A as follows. A of H is a sum from n equal 1 to infinity, psi n, HEN, EN. You see, this is very simple from the point of usual function analysis operator. It is just diagonal with the eigenvalues psi n. And it is evident that it has the desired properties, because the result is Gaussian, it is square integrable, and it is easy to check the continuity in square mean. But if you fix omega, you will get the sequence of values of psi n. Remember, psi n are independent and Gaussian, so they are unbounded with probability 1. This sequence is unbounded with probability 1, so we have no good realization of this A. Moreover, the set where the series converge is of probability 1, but this set depends on H. So when we are discussing strong random operator, we have to be careful with its acting on the elements, and we have to remember that this is not a family of good operators indexed by omega. So what was the main object of he introduced so-called stochastic semigroup consisting of such operators. Let me be more precise. Where 0 is less or equal than S, less or equal than T, such that JSS is equal to identity operator. Secondly, if we have S1 less or equal than S2 and so on, less or equal than Sn, the corresponding random operators S1, S2, and so on, JSn minus 1 Sn are independent. Then three JS plus P, T plus P is equally distributed with JST. And the last one, this is evolutionary property that JS1S3 is equal to JS2S3 applied to JS1S2. You see, these are natural definition, natural properties which we require when we have a semi-group, but you can see the property 4. As we remember, the strong random operators are not bounded operators. So when we define the action of one such operator on another one, we have to be very careful. You can just remember the example which I gave, and in those examples, one can easily produce the following difficult place. Suppose we have random element x, which is equal to 1 over, this is a sequence square, 1 over n, and here is psi n, epsilon n. Such an element. Of course, this is a random element from our Hilbert space because of psi n are independent and standard Gaussian. But if we remember those examples, then AX must be like sum. Here we have such a series, and here we have 1 over n, psi n square, and here an. So if we put here some alpha, we can find such one. For example, that this element lies in our H, but this is not belonging to our Hilbert space. From this point of view, the independency of these two random strong operators is very important. Only for independent strong random operators, Skorokhod was considered stochastic semigroup. And of course, when we have such a semigroup, always we want to have the representation of such semigroup like some Dolian exponent for some semimortal. And he introduced such an operator T indexed by T small, which is expectation of the JOT. And this is due to the properties of strong random operators is continuous operator, and this is a good semigroup. This is a continuous semigroup, and his supposition, main assumption was that T is continuously invertible. Continuously invertible. This was main assumption, and under this assumption, Skorokhod was able to prove that JOT is just a solution of the Hilbert-valued equation with some semi-martingale JOT dz t, where z is again a semi-martingale with the values in the strong random operators. And of course, this z can be found as a following limit. ZOT, ZT is just a limit when we take a partition, and here is a sum from K0 to N minus 1. Here we have J T K plus 1 minus, here is such a sum when we increase partition of the interval 0t. This is a usual way. For example, if you take usual semigroup related to, for example, to exponent, usual exponent, you will get the right answer here. But you see, this is the main assumption. And let me say that this assumption is too restrictive. And we can easily find cases where it does not hold. Let me show you two very important examples. One is related to good stochastic differential equation. Suppose that we have just one-dimensional stochastic differential equation with a good coefficients. I will suppose that the continuously differential have boundary derivatives, and the diffusion coefficients is separated from 0. Then this equation under such good conditions on the coefficients produce us the flow of solutions starting from every point of the space. So one can have a flow of diffeomorphisms related to this equation. Let me index it by 2 points. This is a starting time, this is a final time, this is starting point U. So we have such a flow of diffeomorphism related to this equation. Now let's take Hilbert space H equal to L2R. This is just a square integral functions defined on the space, on the real line. And then one can define finally GSTF for F from here. From U, it is just a shift of F along this flow. This is F phi S T of U. And one can check that due to our assumption on the coefficients, you remember I said that the bounded continuously differential with bounded derivatives, and this is separated from 0. One can have good like Nash or Aronson estimation on the probability density on this distribution. So one can say that this is a strong random operator continuous in square mean, which I in the sense of definition which I presented before. So this is a good family of a strong random operator. You have independency and so on. By the way, this is a really family of strong random operators, because in order to have that this is a bounded operator, we need that its derivative is bounded on all real lines with probability 1. It's not true. So we can produce such an example. So from this point of view, this is a real good example of a stochastic semigroup. But now, what is operator TT? T with index T, expectation of GST is just integral operator. It is integral operator with the density of the solution, and it is evidently is not continuously inverted. By the way, this was mentioned by Skorokhod in his two large papers related to stochastic semigroup. He just supposed to do, maybe he supposed to do something in this direction, but he didn't. The next example shows us even more wrong situation. It is also related to stochastic flows, but to very complicated from the point of view of behavior particles in it, very turbulent stochastic flow. It is so-called Arakia flow. Let me recall you what is it. It consists of the Brownian particles which start from any point of the real line, move independently, then coalesce and move together. Moreover, one can define the Arakia web. So one can start with this particle at any moment of the time. So you can find such a good good from mathematical point of view construction. And let me define a mapping here by phi st as previously. Then one can define this stochastic semigroup related to this map. This is just f from phi st, but it happens that now, if you consider this sum j tk plus 1 related to the increasing partition of the interval minus identity, this sum does not converge in any sense. Doesn't converge. So this reflects the complicated structure of the noise related to Arakia flow or Arakia web. So here a good reference can be work of Cyrilson, and then Lejean and Raymond devoted to coalescent stochastic flows. So one can see that there exists random semigroup of this unbounded strong operators, which demonstrate ugly behavior. From this point of view, one can ask the following question: how it was organized, such a bad semigroup? But also, today I want to present some other question. How to define stochastic semigroup when there is no independence this will be a main question for my talk today. Before to start to answer the question how it is how the semigroup is constructed, let us ask what happens if we lose independence. Can we define the product of these non-bounded random operators in a proper way? And let me give you an example how one can do this. Example is related to the Gaussian noise, and again starting point will be the stochastic differential equation for us. Suppose that still we have the stochastic differential equation. It does not matter it is one-dimensional or not, but for simplicity, let it be one-dimensional. And I will still suppose that we consider the solution which start at point S, time S up to time t from the point U. But now I will consider the special conditioning of our solution. So let me introduce the special sigma defined as J as J. This is this will be a family of some function h which belong L2 0 plus infinity. And sigma of J will be a smallest sigma field which is generated by the integrals from 0 to plus infinity of HS dws. So this is information which we can get about our noise if we know this testing function. Now let us consider the following random operators. Define J as T of F for F, which is from L2 R as before. From U, it is just a conditional expectation of F from here we have phi S T U with respect to this sigma of J. Yeah. So we have such a family. Still, as I mentioned, it is not too hard to check that JST is good random operator in the sense of square root. And one can consider a family. One can consider such a family. But see what happens. Now, due to the general construction of this sigma field, we cannot expect that our operators remains to be independent. We lose this independence. So what we will have instead? What will be a proper definition of the product of such two random elements. Why I am saying proper definition? Because we already have this operator. They are given for us by this formula, and we cannot avoid, we cannot produce our definition. We just have to investigate in which sense these operators are connected one with another. And the answer is following, and it was proved by me in my case that the answer is following. If we have S1, which is less or equal than S3, then we have the following: JS1S3 is equal to JS2S3, and here is a JS1S2, and this is a weak multiplication, weak product. Now let me recall you what is it. Let me recall you what is it via Gaussian variables. Yeah. Let me recall you the definition of the weak product in Gaussian case. If we denote our L2 with 0 plus infinity, L2 0 plus infinity, like new Hilbert space H, and define for all H which belong to H, just short notation. Psi of H will be integral from 0 to plus infinity H of S dws. Then Psi is so-called Gaussian white noise. Psi is Gaussian white noise. Gaussian white noise. In the space H. And if we have some random variable alpha, which is measurable, I will use such a non-formal notation, but it's very common. I will use this notation not only for events from sigma field, but when I will write a random variable belongs to some sigma field, it means that this random variable is measurable with respect to the sigma field, sigma of Psi. Then alpha can be F square integrate. Alpha can be expressed in terms of infinitely dimensional Hermite polynomials like AK1 and so AKN, and so and then I will write HK1 from Xi1 and so on, HKN from Xin, where Xik is just application of Xi to our orthonormal basis. We can express our random variables as follows. And finally, a weak product arises when we just have two products of this. Actually, we have to define only weak products for powers of this one. So just weak product of Xi, for example, Xi1 K1 power Xi E in Ke power is by definition the product where we substitute powers of different xi by Fermi polynomials. hk1 from xi1 and so on, h ki from xi. That's all. We just substitute powers by polynomials, by Fermi polynomials. That's all. But this leads to the very deep theory, and we'll mention it today, to the so-called extended or Skorokhod stochastic integral. It is closely related to stochastic differential calculus, and so on. We have seen that at least in Hauschian case, we can have an examples of non-independent of stochastic semigroups consisting of non-independent random operators where the product is properly defined, and we can expect good properties, and we can investigate those semigroups which I mentioned to you, and get a lot of good properties. So let us ask what we have to do if we have non-Hauschian case. And today I want to present you some construction based on the stochastic calculus. As I mentioned to you, we have two subjects of discussion today. One is stochastic semigroup, another one is stochastic calculus. And what we will discuss now, I will consider some Banach space, real separate Banach space, and probability measure mu on this space, such that I have injection of L2 0 plus infinity into this space, and moreover, all these elements will be admissive shifts for me. Yeah. So I will not to distinguish the image of this injection and elements. From this point of view, always I will say take H from here, but at the same time, it is an element of our Banach space. So that pH will be shift is a shift on H in B, and what we will assume that mu shifted measure mu phi H minus 1 is absolutely continuous with respect to initial measure mu. Even further, I will suppose that it is equivalent. We can easily produce a lot of examples, just taking Hauschian measure with the density, with some good smooth density. We will have such kind of examples. So let me suppose this one, and I will suppose that mu has a logarithmic derivative with respect to each. Mu has a logarithmic derivative with respect to this family H. Then I can consider the stochastic derivative for functions which are defined in the space B. I will call this function by the random variables because From now, I will suppose that our B mu is actually omega p. So I will call this function by random variables, and this is d alpha is stochastic derivative related to this shift. Is stochastic derivative. As always, we have the integration by part formula related to stochastic derivative, and so if we put d alpha h and take the expectation, then we get that here we have expectation of alpha, and I must take logarithmic derivative in the direction h. From this point of view, one can consider interesting sets. Take t, which is bigger than 0, and take such a set of random variables alpha that the stochastic derivatives belong just to subspace L2 0 t. This is a subspace of our big set. So they are equal 0 after the moment t. Consider such alpha. In good examples, we can consider sigma field generated by such alpha, denoted by ft. And now consider the process mt, which will be a logarithmic derivative of this kind. Then it occurs that this process mt has a good property. It is not a martingale, it is not adapted in general to this flow of sigma fields, but if we consider T1, which is less than T2, less regular, and consider the expectation of the difference MT2 minus MT1 with respect to FT1, it is equal to 0. So it has such like martingale property. At this point, 3 years ago, we get an intersection with Professor H. Kuo from Louisiana State University. He visited Kyiv, and we discussed such kind of processes. He found it from other point of view. He called it neo-martingale, because this like neo-martingale property. And now one can try to solve some equations with these processes, and one can try to consider the equation like this one. Here is the logarithmic derivative of x multiplying on the integral from 0 to t. And if x0 is equal to 1, it occurs that when we solve such equation, we will get the density d mu. Here is phi, the indicator of 0t minus 1 d mu. This is a solution. From this point of view, I denote this like a stochastic exponent. This is from integral indicator of 0t. So we just see that our densities under admissible shift of measure mu forms the family of solution to such equation. More, one can ask what happened if we just take random initial condition here. Random initial condition here. And here, let me present you a nice formula which we have here. We will get that the solution xt will be equal to alpha shifted by the phi minus. So this is a backward shift of this 0t, and here multiplied by the previous exponent. And for people who just remember the story about the linear equations with the Skorokhod integral, maybe this formula became to be rather familiar. It was the 1998 when it was 1988 when it was obtained by Rainer Bogdan. At this time he was a PhD student of Hans-Jürgen Ehrenberg. It was obtained a general solution to linear stochastic differential equation with the extended stochastic integral or Skorokhod stochastic integral with the Wiener process. And the formula was exactly following. When we put here random initial condition, we have to move it along the probability space and then multiply on the usual solution which we have when put here just one. Yeah. So you see, the same happened in non-Gaussian case too, but for us it is even more important, not only from the point of view of just equation with extended stochastic integral in non-Gaussian case. It is interesting to see how this formula is transformed in the language of the weak products of the language of product of stochastic exponents. From this point of view, let me recall that generally we have the following solution. Xt, let me put here 3, for example. Xt3 is equal to stochastic exponent related to this indicator, T3. Suppose that we have such a 0, T1, T2, and maybe, okay, T3. Then what we expect? That when we consider our equation here, we can put the stochastic exponent at this point as initial condition. So from this, one can get a very nice formula for stochastic exponents. Our stochastic exponent indicator of 0 T3 is equal to, just forget about this tau 1, T1 is equal to stochastic exponent related to indicator from 0 to T2. Now what we have to do? We have to shift it back by the direction T2, T3. And then after this shifting, multiply on the stochastic exponent from T2 to T3. Okay, so this is the right formula for multiplication in the sense of stochastic calculus of stochastic exponent. We get it for solution to simple stochastic differential equation, but of course it remains to be valid. It can be proved for arbitrary shifts, for arbitrary element of our space. And let me rewrite it again. So what formula we'll have? We have such a nice formula that stochastic exponent related to h1 plus h2 is equal to stochastic exponent related to h1 shifted back on h2 and then multiplied by stochastic exponent from h2. And here is right definition how we can produce weak product for stochastic exponents in the general case. I recall you that this is non-Gaussian case. For example, let me show you the example. For example,
5 minutes more.
Excuse me?
5 minutes more.
Oh, okay. Thank you very much. I just yes, I'm watching. I also have a clock. Okay. So let me give you a good example. Suppose that our mu is measure of the following kind. This is like following. I will discuss it on not on 0 plus infinity, but on 0, 1. It is not too important in time interval now. And here is E minus W1. E minus W1. Let me maybe square here. Yeah. Multiply by Wiener measure, mu0. Yeah? So we have such kind of density, and then we consider everything which I mentioned. Let me show you stochastic exponent now. This stochastic exponent from the indicator ST has a nice form. It will be like usual. This is exponent. Here WT minus WS minus 1/2 T minus S. But due to this term, we will have minus W1 square T minus S square. You see? And you see, due to this term, it is not multiplicative in the usual sense, but in the sense of this new weak product related to this measure, it is multiplicative. So now we are able to produce the definition of stochastic semigroup based on this calculus. So we solve the problem when we have dependence inside of the stochastic semigroup, and the right definition will be that T1, T3 must be equal to J, T2, T3, and here is this is generalized weak product which we already defined, T1, T2. So we can consider families of such random operators, discuss the equations with them, and do stochastic calculus for them. This is my point for today, and thank you for your attention.
Thank you for a very motivating talk. Questions, please.
So probably I have not a question, but a small remark, a motivating question for the future. So may I?
Yes, you are welcome, please.
Yes, yeah. So seemingly, even on the level of Gaussian case, have you considered SDEs with fractional Brownian motion instead of Brownian motion?
You see, there are a lot of work where we can consider in this framework. We can consider stochastic and partial stochastic differential equation with different Gaussian processes. But what we need, we consider usually equation like this one. dxt is equal a xt plus bx dmt, and we want to put here something new. Yes, then we have to define this integral, and if we work in the Skorokhod sense, then we can proceed as follows. We can associate our MT, our Gaussian process, with some operator, with some integral kernel. Yes, and it will look like this. This will be in our previous notation white noise from some H, maybe R, from indicator of 0t. 0t. Then we will face a situation with the Skorokhod integral, and we will rewrite this integral term when we will integrate as Skorokhod integral from R B multiply on this or R star. I don't remember, but it is not necessary.
So we reduce everything back to Brownian motion.
This is not Brownian motion, because of this R can be very bad, like for fractional Brownian motion. It's blowing up near diagonal, so we will have a lot of difficulties related to this plot. But I mean that such a kind of equation, people consider such kind of equation. Always when we fix this R, we get new troubles. So some new efforts must be done.
So my further question would be, so now if we want to have something like generalized gray Brownian motion, which is conditionally Gaussian, but as a general not Gaussian, so we can try this approach with
yes, surely, and as far as I remember, Yaozong Hu from Kansas, now maybe he moved to Canada, but before he was in Kansas, and he did something, some even partial stochastic differential equation with fractional noise, exactly using Gaussian stuff.
Okay, thank you.
You're welcome.
More questions, please. We have time for maybe 2 more questions. Okay, maybe then I will ask a question. Summing up, can you please say what from your point of view is the most important in your talk today?
I think that this idea to formulate weak product in the non-Gaussian setup with the help of this formula that here we have H1 phi minus H2 H2 that is equal to H1 plus H2. So this is a exactly weak definition of the weak product in non-Gaussian case for stochastic exponent. And of course, I did not show the technical details, but it can be expanded not only on stochastic exponent, of course. So the idea that instead to define a weak product, as we did it in Gaussian case, using algebra and calculating the Hermite powers, we just do analytical things. We just move one variable back and multiply it. Yeah. So this is the main idea.
Thank you very much. If there are no more questions, let us
Probably one more remark.
Yes.
Once again, that in quantum mechanics there are such time-ordered exponents or something like this, where the time ordering is important in constructing like a kind of this Feynman path integrals.
Okay, thank you for this remark, because of course all this thing is related. You remember one of the most easy calculated example here is just perturbation of Gaussian measure by some density. Exactly as in quantum physics we did. So I think that I will look on this time-dependent exponents. Thank you very much.
Thank you for your interesting talk. Thank you.
Thank you. So if there are no more questions, let us thank the speaker again. Good.